and we have done weak acids and weak bases. Now we're going to move on to salts. Now, salts result from the neutralization of an acid plus a base. Ions are the conjugate base plus the conjugate acid. Remember when we talked about neutralization reactions, we have an acid plus a base in 1211. We're going to produce a salt plus water. Well, now we need to talk about the salts because not all salts are created equal. So what we see here is sodium A minus will dissociate into these two species here. Now, this is the conjugate of a strong, and the strong is sodium hydroxide. That's a base, so this is the conjugate acid. And remember, we talked about relative strengths. The stronger the acid, the weaker the conjugate. While really strong acids or bases, the conjugate is neutral. It's basically useless to us in terms of the pH. However, this is the conjugate base of a weak acid. So, depending upon how weak the acid is, the conjugate base could be very strong. So then we can set up the equilibrium. So notice this is the conjugate base. We end up with a basic solution. On the other hand, if we have the basic salt, it's going to dissociate into the conjugate acid of the weak base and the conjugate base of a strong acid. And again, and our strong acid here is HCl. So this one is going to be neutral because the conjugate in anything that's strong is really not helpful, so we're going to worry about this one. And so since this is an acid, even though it's a conjugate acid, it's going to produce an acid in solution. So the bottom line on this is that salts are not neutral. The only salts that are neutral are the ones that result from a strong and a strong. So we're going to have to look at those in more detail. So how do we do this? Well, remember that the Ka times Kb is equal to Kw. So if this is acetic acid and there's its Ka, this would be the conjugate base of acetic acid. So this one would be the Kb associated with the acid. So what we can do is set the Ka times the Kb is equal to Kw, which is 10 to the minus 14th, and solve. So we find out that this Kb is 10 to the minus 14th. Water's 10 to the minus 14th. The base is 10 to the minus 10th. So while it is still basic, it's a very weak base because acetic acid is a relatively strong weak acid, so the base would be comparable in terms of the weakness. So this goes on a regular basis with everything else. Bicarbonate and carbonate control in the pH of your blood. It also works in washing soda. So what happens is remember we showed you that amphoteric of this form right here. It can go both this way and you can get the H2CO3. And so this is where we look at, this is your blood gas because you're breathing CO2. CO2 plus water, guess what gives you carbonic acid? So this is one of those interesting little chemistry thing that moves across a variety. Now, here are some pictures of salts. This is using a universal indicator. So green is neutral. Blue or purple, depends upon which universal you get, will be basic. And red will be acidic. So this one is slightly acidic. This one is very acidic. These are basically neutral. They do not have an example of a basic salt. But think about it this way. Which salt do you think is the most common? Basic, neutral, or acidic? Your hint of the day is look at your KAKB sheet. Who has more KAs? That means that there are more conjugate bases associated. So actually, most salts are going to be slightly basic because most species, there are more acids than there are bases. So that brings us to looking at our sheet. And if you look on your sheet, you will find that iodic acid is right here. So we're looking for the conjugate base, which means we want I3 minus. Now, my recommendation, I'll do one more. So conjugate base acid of urea. Urea is a goofy little structure. Here it is. So that, it happens to be a base form. This one happened to be an acid form. So the conjugate acid of this base is NH 2COH plus. Now, you could put the H at the front. That would have been fine. Doesn't matter. Bottom line is you need to be able to ID these. So I would pause it here and go take your Ka chart and try to fill this out and then check. I will continue on. The conjugate acid of pyridine is C5H5NH plus because the acid, conjugate acid means it acted as a base, so it picked up a proton. Conjugate base means it lost a proton, so there's benzoic acid. Cyanic acid is CNO. Hydroxylamine drives people insane because the proton tends to go on the nitrogen, not on the OH. But again, it doesn't matter. Hydrazine, you can put the proton on either side. I'm only concerned with that you gain the proton. You'll have a couple of these on the exam. They'll probably be multiple choice, matching, fill in the blank. No, fill in the blank kind of sucks for these online. So, bottom line is you will be asked to ID them. C6H5O minus, HSeO3 minus, and HC2H2O4 minus for melanic. Now, notice if I've gained a proton, I gained a positive. If I lost a proton, I gained a negative. Well, I lost a positive, which leaves me with a negative. So when you look at these, the charge is as critical as the loss or gain of the proton. Okay. So with salts, you should be able to identify whether they're acidic or basic without performing any calculations. Now, trust me, we will do some calculations shortly. But right now, I want you just to look at them. And you will have one like this on the test. And so what we get is we're going to dissociate into nickel 2 plus and bromine minus. Now, we don't care that there are two bromines. We care that it's balanced and neutral for the original compound, but once we're looking at the acid base, we don't care. So, easiest thing to do is start with the one you know, and the one you should recognize immediately is this is the conjugate base of HBr, which is a strong acid. So if it's the conjugate base of a strong, it is neutral. Okay, so it's useful. That means this one has to be the conjugate acid of a base. What base? Well, when in doubt, slap on hydroxides. If it's basic. If it's acidic, then you slap on protons. So we know that this is a weak base. So the conjugate acid would be acidic. So if we look at acidic plus neutral, this salt will be acidic. And that's really all you have to do. Is you don't have to know what the bases are, what the acids are. What you do have to know is you have to know what's strong. And so you have to memorize that chart. So this one is going to dissociate into sodium ion. And this one's going to dissociate into whatever this is. I don't remember what it is, and I really don't care. This is the conjugate acid of sodium hydroxide, which is a strong base. So this one is neutral. Now, I'm going to tell you right now, if I was doing this face to face, you would have a problem like this on the exam, that you would write all this stuff out. But because we're doing it online, looks like one of those multi-selects. Like, is it acidic or basic or neutral, and why? Just warning you. So this one would be the conjugate base of HC7H5O2, which I don't know what it is, but I know it's a weak acid. Therefore, this one will be basic. So if we have a neutral plus basic, then this salt is basic. And these don't require any calculations at all to figure out. You just have to know what's a strong and what's a weak. So this one is kind of more interesting. Will the salt of this species result in an acidic, basic, or neutral solution? Well, it's going to dissociate into potassium and HC4H4O5 minus. Well, this one here is the conjugate of KOH, which is a strong base. So since it's the conjugate of a strong, then it is neutral. So what do we do with potassium? We ignore it. Okay. Now this one creates a problem because this can actually act as an acid. It has a proton to give up. It has already given one up, so it is a Ka2. On the other hand, it's a negative, so it could pick up a proton. It's already got one, so it's the Kb2. So remember, Kb start with fully deprotonated. Ka start with fully protonated when you're looking at them. So we can take our table and we can look at it and go, oh, wait, Ka2 value, that's 8.5 times 10 to the minus 7th. That's your Ka2. But if you look at the table, you don't have a Kb2. So you're going to have to calculate the Kb2. Well, here's the thing. All right, we're going to take a side trip. And this side trip is actually pretty critical. And here's our side trip. Let's look at some acids. This is a diprotic acid. So we're going to deprotonate the first time. This is your Ka1. And then we'll start with HA, and then we'll go to H plus A minus. 2 minus, sorry. This is your Ka2. Everybody good so far? Well, if we start with the proton, the base form, we're going to start with the fully deprotonated form, add water, and we're going to produce HA minus plus OH minus. This would be my Kb1. Wait, why is it your Kb1? Because you're gaining your first proton. The Ka1, you're losing your first proton. So then we have HA minus plus H2O is going to produce H2A plus OH minus. Again, we know this is a basic because we end up with a base. This is Kb2. Now, if you look at it, guess what? In order to cancel, these pair up and these pair up. So, remember our rule of Ka times Kb is equal to Kw, right? So we actually need the Kb2 value, right? Whoops, went too far. Maybe we'll go back. Okay, we need our Kb2, so let's go look at this. So that means that my Kb2 has to be multiplied by my Ka1 to get Kw. Now, I'm going to walk it through with the expression to show you, and then we'll do the actual math. So the Kb2 is HA minus OH minus divided by A minus, 2 minus. Okay, or my Ka1 is H plus times, oh wait, I need my, Yeah, I did KB1. I hate it when a plan doesn't come together. So let me start over. I need KB2, which is H2A times OH minus. KB1 with Ka2 will work. I just want to do this one. This is your HA minus. That's your KB2. Ka1 is H plus times HA minus yields H2A is all equal to Kw. So if you look at it, the HAs are going to cancel, the H2As are going to be canceled, and you're left with H plus times OH minus is Kw, which is what we need. So if we're looking for Kb2, it's going to be equal to Kw divided by Ka1. All right, let's go back and actually play with the numbers here. Let me see if I can find the color again. All right, so this is going to be Kb2 is going to be Kw divided by Ka1, which is 10 to the minus 14th. And if we go look up the Ka1 value, it's 1.5 times 10 to the minus 2. So my Kb2 is 6.67 times 10 to the minus 13th. So if you look at it, your Ka2 is going to be greater than your Kb2. So this salt is acidic because the A is greater than the B. Now, that doesn't actually always occur. Now, one other thing I want to point out here on my little side note is I highly recommend you take the time to do a tetraprotic acid and prove to yourself that they invert. So your Ka1 will go with your Kb4. Your Ka2 will go with your Kb3. Your Ka3 will go with your Kb2. And your Ka4 will go with your Kb1. Now, my recommendation is you work that on the side. You only have to do it once just to make sure you prove that you understand the relationships, and it will make your life easier if you're comfortable doing that. Okay? So, let's move on to the next problem. We have a salt of ammonium fluoride result in an acidic basic solution. Well, again, it's going to break up into ammonium ion and fluoride ion. Now, this is the conjugate acid of ammonia, which is a weak base. So it is acidic. This one is the conjugate base of HF, which is a weak acid. So it is basic. Wait a minute. So we have to know how acidic it is and how basic it is. So if this is acidic, this is a Ka. So the Ka is going to equal to the Kw divided by the Kb, which the Kb for ammonia is 1.8 times 10 to the minus 5th. So that gives you a Ka of 5.56 times 10 to the minus 10. On the other hand, the Kb here is going to be equal to Kw divided by Ka, which the Ka for HF is 6.3 times 10 to the minus 4. So the Kb is 1.587 times 10 to the minus 11. So in this case, the Ka is actually greater than the Kb, so this salt is acidic. So the bottom line is if you have one that's neutral, then you know what it is and you don't have to do any math. But if you have both, then you're a given. Now, one other little side note, and I'm going to change colors here. So if we have something like sodium chloride, this is the conjugate acid of a strong base, sodium hydroxide, which is strong, so it's neutral. Chlorine is the conjugate base of HCl, which is a strong acid, so it's neutral. So in this case, two neutrals make a neutral salt. But most salts are not neutral. Okay? Alright, so that brings us to, wait a minute, we can do exactly what we did with weak acids and weak bases with salts. So what concentration of a salt of methylamine chloride will yield a solution with a pH of this species? Okay, I don't want to write this, so I'm going to call this methylamine chloride, and because it splits here, it's my H, because it's actually acidic salt. Now, I know it's acidic salt because when it's split it up from the chloride, then it's a positive. So that tells me. Also, if you look at your pH, it's less than 7, so it's an acidic salt. So we'll do my H is going to dissociate into my methylamine plus H plus. ICE. So we're looking for the concentration here. We know we have 0 here. We're going to lose some amount. We're going to gain the same amount. So our final volume is X minus delta, delta, and delta. So right now, with our K, this is what? This is a Ka. We have two unknowns, two variables, and that can't fly, because what we're looking for is, we're looking for X. So X is our unknown. So we have to figure out delta. Well, guess what? We know that the H plus concentration is going to be equal to 10 to the negative pH, which means it's 10 to the negative 5.95. So if it's 10 to the negative 5, that means that the H plus concentration is 1.122 times 10 to the minus 6 molar. So everywhere we see the delta, we can put 1.122 times 10 to the minus 6. For both of these, we get 1.12 times 10 to the minus 6. So our Ka, we don't have a Ka for this species, but we do have a Kb because it is conjugate acid. So the Kb of our species is 4.8 times 10 to the minus 4. We got that from our table. So on a test, I'll give it to you. So that means my Ka is Kw divided by Kb. 10 to the minus 14. This is 4.8 times 10 to the minus 4. So my Ka value comes out equal to 2.0833 times 10 to the minus 11th. So what we end up with is 1.122, I don't know why I don't 2, times 10 to the minus 6 squared divided by X minus 1.122 times 10 to the minus 6 is equal to 2.0833 times 10 to the minus 11th. Okay, so we go over here and we do the ugly A word, which is algebra. So we end up with 0.0604273988 is equal to X minus 1.122 times 10 to the minus 6. That means we move the negative 6 over, so X is equal to 0.06042852 molar, which if you're using 4 significant figures, that means my MaH plus concentration is going to be 0.06043 molar when I'm done. Now, that can be done with a weak acid. Okay, it really can't be done with strong acid. But we can do this, what's the concentration, with anything we want. And it really doesn't matter. We get the same value regardless. Okay, so what concentration of potassium hypoiodite will yield a solution with a pH there? We have a basic salt, which means that HIO will be an acid. So it has a Ka value of 2.3 times 10 to the minus 11th. So when it dissociates, it's going to dissociate into K and IO minus. This is the conjugate of a strong, so it is neutral. So what do we do with it? We ignore it. This is the conjugate base of HIO, which is a weak acid. So it's going to be basic. So we have IO minus. Since it's basic, we're going to add in H2O because we get HIO plus OH minus. So what we're looking at is we get an RSCE table. So we're looking for the concentration here at 0, 0. Whoops, minus delta. I don't want to use the same. Plus delta. Plus delta. You can use X, A, B, C, whatever floats your boat. Again, the hydroxide ion concentration, remember, is equal to 10 to the negative pOH. We're given the pH. So the pOH plus the pH is equal to 14. So our pOH is equal to 14 minus 11.4, which comes out to be equal to 2.6. So if we go 10 to the negative 2.6, that gives us a value there of 0.002512, which means that the delta anywhere we look is 0.2512 molar. That's a 0. Okay, so that means that my Kb, and it is a Kb because we have a hydroxide, is going to be equal to 0.002512 squared, because that's our Kb is HIO times OH minus divided by IO minus. And so it's equal to X minus 0.002512. The Kb is equal to Kw divided by the Ka, and we're given the Ka of 2.3 times 10 to the minus 11. Not that you can really read that. That's goofy. You erase that and rewrite it. Okay, so that means, remember, this is Kw is 10 to the minus 14th. So this value here is equal to 4.3478 times 10 to the negative 4. Okay, so what we do when we get our math is we end up with X is equal to 0.01702 molar. What was the question? Was the concentration of the salt. Okay, so the initial concentration of the salt of potassium IO3 is this value right here. Now, my recommendation is you work these through and make sure you get the exact same numbers that I get. Okay, now we have 2 more to do. I would actually pause this, work these problems, and come back and check them. But it's up to you. Sodium benzoate is preservative in foods. Calculate the pH of a 0.5 molar solution of sodium benzoate. Well, sodium, remember, is the conjugate of strong. So it is neutral. So the only one we're worried about is the species here. If that's the conjugate acid, then this will be the conjugate base, so we're dealing with a base. So C7H5O2 minus will react with water to produce HC7H5O2 plus OH minus. ICE, in this case, we're given our concentration 0.02500 minus X plus X plus X 0.025 minus X, X, and X. Now, I would need benzoate as our Ka, which is 6.3 times 10 to the minus 5. That's the Ka of benzoic acid. So we want the pH Alright, so this is AKB, which means it's going to be X times X divided by 0.025 minus X. And the KB is going to be 10 to the minus 14th divided by 6.3 times 10 to the minus 5th, which is equal to 1.5873 times 10 to the minus 10th. So when we set this math up, we're going to end up with an equation of X plus 1.5873 times 10 to the minus 10th X minus 3.96825 times 10 to the minus 12th is equal to 0. We're going to run it through the poly function, and we get 1.99196 times 10 to the minus 6th, which is equal to the hydroxide ion concentration, which means my pOH is equal to 5.70, which means my pH is equal to 8.30, which makes perfect sense because we know this is a basic solution. Our pOH is less than 7, so our pH should be greater than 7. So the other thing I want to do, and I didn't ask you to do this, but let's look at the percent ionization. Well, the percent ionization will be the HC7H5O2, in this case the conjugate acid, divided by the C7H5O2 minus. So this is going to be equal to 1.99196 times 10 to the minus 6 divided by 0.025 times 100. I ran out of space there. So since I didn't ask for that before, I'm going to have to real quick calculate it. E to the minus 6 divided by 0.025 times 100. So what we actually get is 0.00798%. So this actually has a very small percentage, but it is used as a preservative in food. So if you read labels, you will have noticed it. So, well, last one, ammonium nitrate is used to make fertilizers and making matches. So, ammonia is a base, so it has a Kb value of 1.8 times 10 to the minus 5th. This is a salt, so it's ammonium nitrate, so NH4NO3, which means it's going to dissociate into NH4 plus NO3 minus. This is the conjugate of a strong, so it's neutral, which means this one's going to be acidic. So we're going to have NH4 plus yields H plus NH3. It's an ICE table. We have 0.15 molar, 0 minus X plus X plus X, 0.15 minus X, X, and X. So we end up with Ka, which we have to get from the Kw divided by the Kb, which means we get 5.55556, it's repeating, times 10 to the negative 10th. So when we set up the problem, we're going to get x squared divided by 0.15 minus x is equal to 5.5556 times 10 to the minus 10th. So we're going to move up here. We'll end up with x squared plus 5.5556 times 10 to the minus 10th x minus 8.333 repeating times 10 to the minus 11th is equal to 0. So that means we just run it through the poly. We get 9.12868 times 10 to the minus 6. Remember, this is the H plus concentration. So we just take the negative log of it. Times 10 to the minus 6 is equal to the pH, which means my pH is equal to 5.039. 59, which means 2 places after the decimal, pH is 5.04. So this ammonium nitrate is acidic. So we've done weak acids, we've done weak bases, and then we've done conjugate acids and conjugate bases in the form of a salt. So all of these are fair game. I want you to look at how they're alike, and then I want you to look at how they're different, and you'll see that they're all pretty much the same thing over and over. The next section we do, I think, a couple more problems, but the end section in this chapter is Lewis acids and bases, and they operate on a totally different theme. So we're good to go here.